Welcome back to our first simulation tutorial. Today I'm going to be using a half-wave dipole to demonstrate the simulation environment in SuperNEC. So to keep everything mathematically simple, I'm going to be working with a frequency around 300 MHz. 300 MHz gives us about 1 meter electrical, so half-wave dipole, half a meter length dipole. So I'll be showing you how to explore the radiation pattern of different antennas, how to see the VSWR of your simulated antenna, see the current distribution, and obviously I'm just going to show that the simulation is working correctly. I'm going to show you on the VSWR how the characteristic impedance of our half-wave dipole is the standard 73 plus 43J omega. Let's get started. In our last video, we learned how to install SuperNEC as a package on our computer and use it through MATLAB. If you haven't seen that video, please pause right now and follow up on that. And then once you're back, we can learn how to start simulating. So I have the SuperNEC environment open in front of me right now. And I'm going to add an assembly. So you'll see assembly structures. I'm going to start with a simple dipole. So I'll go through to wire antennas, and you'll see right there's SN dipole, there's a fat dipole, but we're just going to start simple. So we're working with a half wavelength. So you'll see here N1 is set to be a quarter of a wavelength, and N2 is a quarter of a wavelength. And it's important to add a source, otherwise your SuperNEC program will not run. So I'm just going to add a voltage source of 1 volt. And there you'll see a little wire dipole, one of the simplest one. Go on to simulation settings. Okay, there. So first thing we're going to do is we're going to be setting up a frequency range. So this is standard MATLAB. So because we chose 300 MHz, I'm going to make mine from 280, increment by 5 MHz, up to about 320. Okay, so to start off simple, I'm just going to add one radiation pattern of 4 degrees increment. What you can actually do is you can add any one, the XY plane, the YZ plane, to show you that beautiful right angle between the electric and the magnetic fields of your dipole, but for now I'm just going to go with a basic 3D pattern to show you how to start off on the SuperNEC. Okay, so after that we can press simulate. We'll have to create a file for our simulation, so I'm calling it dipole demonstrate. There we go. Okay, so now we have a command window running. It's running for each of the frequencies, and you'll see here this is the frequency range we've set up, incremented by 5, and we'll plot it like this. This is our current plot. So you'll see on our current plot there at the center is where most of our current is, and at each end that's where our current is going to be pretty close to 0, as is standard with a half-wave dipole. But obviously if you plot later on your voltage, you'll see actually that the voltage maxes out at our ends, which is pretty typical for this type of basic wire and antenna. But yeah, so moving on from that, let's go to something more interesting. Let's go to the excitation models. Okay, plotted for all frequencies, and there we go. You got a Smith chart of your excitation model. Now if you look at the very top of that semicircle, you'll see the real and imaginary parts multiplied by the characteristic impedance of our dipole, 50 ohm in our case. You'll see that it'll match the characteristic impedance that we expect from a half-wave dipole, namely 73 plus 43J ohm. Now we can begin considering a lot of stuff. You can do to the Smith chart, phase, you can put pretty much anything here. If you look here at the VSWR, yeah, it's not a super great antenna, but that's because it's slightly under resonant. Go to your radiation plots, pick one of them and plot it out. And here we will actually see that classic donut shape of a half-wave dipole. And you can have different formats. It shows you basically everything, and to make it a little more interesting, you can there we go. Sorry, you can actually take slices of this plot, press 2D, and there you actually have that beautiful characteristic well, no other way of saying it, butt-shaped radiation pattern. And that should be enough to get you started. We'll be working with an LPDA to actually show you the more in-depth things you can do with SuperNEC in the next couple of videos. So this is where it's going to get a little hardcore. I'm hoping you'll stick with us. If you want to get more into SuperNEC, do a little more of the simulations, please remember to subscribe, click that bell button, and I'll see you in the next video. Bye!